Hi, everybody, and welcome back for Lesson 3 from Unit 5, which is about the first derivative test. So we have one learning target for today, and our target for today is I can use the first derivative to determine the location of relative, or in other words, local extrema of a function and justify my answer. So there are going to be a couple different components today. We're going to need to define what it means to have a relative or local extrema, and then we're going to be using the derivative to find those values. And then the second component is that we're going to be justifying our answer. And how you explain or justify your answer, it needs to be like using mathematical notation. And so we're going to be very specific about what it means to justify your answer for a relative or local extrema. So let's start with defining what a relative or local extrema is. The maximum and minimum values, which we often abbreviate max and min, of a function are called the extreme values, or the plural of that would be extrema of the function. In this lesson, we're going to be learning how to use the first derivative to find these extrema. So let's start with just visually looking at a graph and identifying the extrema of the function. A relative or local minimum is going to be a low point on the graph. So I often call these valleys in the graph. Now, a relative minimum cannot occur at an end point of the graph. Later on in this unit, we're going to be learning about what are called absolute maximums and minimums, in which case those could occur at an endpoint. So the reason that I'm pointing out right now that a relative or local minimum is never going to occur at an endpoint is to clarify the difference between a relative minimum versus a global or absolute minimum. All right, if we look at this graph and we look for low points or valleys, there would be a low point on the graph right here. There would be another low point on the graph right here. You can see that that's a place where the graph goes downhill and switches to uphill. That's a valley, a low point. Same thing here. Those x values would be the locations of relative minimums. And so the first location would be at -3, and the second location would be at +2. So we would say x equals -3 and +2 are relative minimums, and we could define that as because the derivative or the slope of the function changes from negative to positive. So if you kind of use your imagination, when the slope switches from being negative or going downhill to being positive and going uphill, we're going to have a valley. The same thing here. When the slope switches from negative to positive, we're going to have a valley. Now let's talk about what are called relative maxima, or high points on the graph. So a relative maximum is going to be a high point on the graph. I like to call these peaks. So if you imagine like mountain peaks, these would be like the peaks on the mountain range. We're going to have several different maxima on this graph. The first one is here, the second one is here, and the third one is here. So if I said list the locations here, we would say at -5, at 0, and at +4, we have relative maxima. And again, this can be defined by kind of the behavior of the slope. You'll notice that every time we have a maximum, the slope changes from positive to negative at that spot. And that's what allows us to kind of have that peak, that top of a hill, is that we change from going uphill to downhill. So we would say because f prime of x changes from positive to negative at that value. Now, it's really important to also note that a relative maximum also cannot occur at an endpoint. So when we eventually start talking about relative, no, sorry, not relative, absolute maximums and minimums, then we are going to consider the endpoints as potential locations for those values. So it's important to note that when we're talking about relative maximums and minimums, we are not looking at the endpoints of a graph. Now, when we say, for example, look at this graph and look at the open interval containing the value, what we mean is that we are not including the endpoints of the interval. So in other words, you're going to find the max or the min. So the C value is going to be your max or your min. Location. When you find that value, it's going to be somewhere inside of the interval and not at either of the endpoints. And that is just to emphasize one more time that when it comes to relative extrema, we're not considering the endpoints as potential locations for a relative extrema. As we get towards, again, absolute or global extrema, those endpoints will come into play. So we'll talk about that in the future, but it's really important to understand that for relative extrema, maximums or minimums, we do not look at endpoints. Okay, now how can we find these values if we don't have a graph of the function? Well, what we're going to do is we're going to look at the first derivative. All local, or in other words, relative extreme values occur at critical points of a function. So they're all going to occur at places where the derivative is equal to 0 or the derivative is undefined. And we can confirm that by comparing it to what's happening on this graph. At this point, the derivative would be undefined because there's a corner. At this point, the derivative would be 0, the derivative would be 0, the derivative would be 0, and the derivative would be 0. So all of these maximums and minimums are going to be places where the derivative is, where not the derivative, where the function has a critical point, which means the derivative is 0 or undefined. Now, we can use that to our advantage in order to identify these points when we don't have a graph. So we're going to use something called the first derivative test. If your first derivative, so f prime of x, changes from negative to positive at a certain value c, then your function has a relative minimum at that value. And if we kind of picture this in our head, changing from negative to positive means you're changing from having a negative slope to having a positive slope. And you can see that at the point where we switch, there would be a minimum on the graph. Now, a relative maximum is going to occur at a place where the first derivative changes from positive to negative. So it's still changing signs, it's just that instead of changing from negative to positive, we're changing from positive to negative. And this should say maximum. I apologize, this is a typo in the notes here. So we're going to have a maximum if our derivative changes from positive, meaning it was going uphill, the original function, to negative, meaning the original function was going downhill. At the very tippy top there, where it does that switch, we would have a maximum. Now, it is also possible that we have a place where we have a critical point. So we have a place where we have a derivative that's 0 or a derivative that doesn't exist, but the derivative does not change signs there. If your derivative, f prime of x, does not change signs at a certain value, then your function has neither a max or a min there. For example, if an example of a function where this happens is the x cubed function. If we think about the x cubed function, there would be a point right here in the middle where there would be a horizontal tangent line. The graph kind of flattens out. So there would be a critical point there. The derivative would be equal to 0. But there isn't a max or a min. In other words, if you figure out that your derivative was positive and then continues to be positive, there is no max or min there. Or if you figure out that your derivative is negative, meaning the original graph had a negative slope, and then continues to be negative, there is no max or min there. So if we do not change signs, we know that there is neither a max or a min. Now let's use this idea to actually find the maximums and minimums by looking at a function. So here are the steps for finding relative extrema. First, we're going to find the critical points of f of x. So in other words, we're going to find the derivative and then we're going to make it equal to 0 or determine locations where it's undefined. Then we're going to make a sign chart. Now you may remember that we've actually made a sign chart before. So we've made a sign chart that helps us visually organize the signs of the derivative, which helps us picture the graph of the original function. We did this when we were finding whether a function was increasing, decreasing, or the locations of the critical points. And then once you've done that, you can see kind of where the derivative changes signs and identify the extrema. Finally, you're going to justify your answer using f prime. So you want to actually explain your reasoning by referring to what's happened to the signs of f prime. So let's try this. If we're given the function f of x is equal to 2x to the fourth minus 4x squared, and we're asked to identify the x coordinate and classify the relative extrema of the function, justify your answers. So first step is going to be to find the derivative. So the derivative of this function would be 8x to the third minus 8x. And we're going to set that equal to 0 in order to find the critical points. Now, because this is a polynomial function, we're not going to have any locations where the derivative is undefined. So we're just going to stick to where the derivative is equal to 0 here. If we factor out an 8x, we get x squared minus 1. And we can continue to factor this, and that's going to give us x plus 1 times x minus 1. Now that means that we have three separate x coordinates of critical points: 0, -1, and +1. Using those values, we're going to make a sign chart. So the beginning of the sign chart would be -infinity. And then if we were to put these numbers in order, it would go -1, 0, +1, and then infinity. And we're going to use those numbers to create the dividing lines of our sign chart. Now, what we're going to be doing is we're going to be looking at the sign of f prime for each of these sections. So let's start by choosing a number in between -infinity and -1. If we were to choose a number, I would choose like maybe -10. If I were to substitute that into the factored form of the derivative, which I think is always easier than trying to plug it into the original form of the derivative up here, I'm going to get a negative number times another negative number times another negative number. And three negatives make a negative. So this part of the original graph would have been going downhill. It would have been decreasing. In between -1 and 0, I would maybe choose like -1/2. If I plug that in, I get a negative times a positive times another negative, which means my final answer would be positive. So the original graph here would have been going uphill. And next, if I choose a number in between 0 and 1, like +1/2, and I plug it in, I would get a positive times a positive times a negative, which means I get a negative final answer. So the original graph would have been going downhill. And last but not least, if I choose a positive number between 1 and infinity, like maybe 10, I would get a positive times a positive times a positive. All together, that makes a positive. So this would have been going uphill in the original graph. So if you kind of use your imagination and you imagine the kind of visualizing this, when we switch from going downhill to going uphill, this point right here would have been a minimum because the graph is switching from downhill to uphill. There would be another minimum here at the +1 because the graph is again switching from going downhill to uphill. So you're going to have a valley, a minimum there. If we're thinking about a maximum at 0, the graph is switching from going uphill to downhill. So there would have been a max here. Our job now is to list that information in a neat and organized way and make sure to justify our answers. So let's start with the minimums. We would say f of x has relative minimums at x equals -1 and +1 because f prime of x changes from negative to positive. Now, if we think about the maximums, we would say f of x has a relative maximum at x equals 0 because f prime of x, the derivative or the slope, changes from positive to negative. So again, we have to justify our answers and explain our answers using what's happening with f prime. Now, just like before when we were talking about increasing, decreasing, and critical points, another common prompt for these types of questions is a situation where we are given the graph of f prime. So it's very important to realize here that we have the graph of the derivative that we're looking at. What that means is we need to change the way we're thinking about maximums and minimums here. A lot of times, students do not pay attention to which type of graph they have. So they might look at this graph and go, ooh, peak, maximum. Ooh, valley, minimum. However, we need to remember that we're trying to identify the maximums and minimums of the original function f of x. And this is not the graph of f of x. This is the graph of f prime. So step number 1 is going to be to find the critical points. And I'm going to circle them on the graph. My critical points would be at -2, +2, and 5. And the reason that those would be my critical points is because those are the x-intercepts on the graph of the derivative. And we need to remember that the x-intercepts on the graph of the derivative are the critical points of the original function. Then I'm going to look at my derivative. Anything that's below the x-axis would have been a negative slope of the original. And anything that's above the x-axis would have been a positive. So the next thing I'm going to do is label. Anything that's below would have been a negative slope. So this would have been a negative slope, changing to a positive slope. I went from below the x-axis on the left side of this critical point to above the x-axis on the right side. Now for this critical point, I'm below the x-axis on the left side and below the x-axis again on the right side. So those will both have been negative slopes. Oops, I forgot to circle this critical point. So sorry, guys. Those would have both been negative slopes on the original. Going back to where x is 0, we have a positive slope on the left side because we're above the x-axis and a negative slope on the right side because we're below. Then on the left side of the 5, we would have a negative slope switching to a positive. So if I were to make my sign chart for this problem, my values would be negative infinity, and then -2, 0, 2, 5, and then infinity. Now I'm going to use what we just talked about, where the below parts are the negative slopes and the above parts are the positive slopes of the original function to fill in this chart. So on the left side of the -2, we decided that the original graph had a negative slope because it's below the x-axis. In between the -2 and the 0, we decided the original graph had a positive slope because it's above the x-axis for that section of the graph. In between the 0 and the 2, we decided the original had a negative slope because this is below the x-axis. In between the 2 and the 5, we decided the original continued to have a negative slope because it's below the x-axis. And after the number 5, we decided the original has a positive slope because it's above the x-axis. Now, using your imagination, you can kind of picture where the maximums and minimums would be. I think, for me at least, I can visually see if we go from downhill to uphill, this would have been a min. And there would be another min right here where we're changing between a negative slope and a positive. There would also have been a max right here because we're changing between positive and negative. And right here at the positive 2, where we have a downhill and it stays downhill, there would have been neither a max or a min there. Now, all that we have left to do is list our information in a neat and organized way. So we would say that f of x, the original function, has a relative min at x equals negative 2 and positive 5 because the derivative, which is f prime, changes from negative to positive there. Now, let's talk about the maximums. So we would say the original function, f of x, has relative maximums at x equals 0 because the derivative, or f prime, changes from positive to negative, and f of x has neither a max or min at x equals 2 because f prime of x, the derivative, does not, oops, you can't see what I'm writing, I'm so sorry, does not change signs. All right, that is it for us today. Thank you guys so much for watching, and I will see you for some practice in class next time.